Hello, everyone. Good morning, good afternoon. My name is Carmen Guguta, and I'm your host from Technobis. Together with me today, I have Pierre-Louis Lagueux-Tremblay, our presenter today. The webinar today, it will be on streamlining process development of Aldol reactions with the ReactALL. Before I introduce officially the presenter today to you, I would like to tell you that this webinar is being recorded and it will be made available to you all most probably tomorrow. You will receive an email with a link where you can review or watch this webinar as well. You can download the slides. You are muted, but if you have any questions, please make use of this platform, the Q&A chat section, and write to us your questions. I will read them at the end of the webinar to Pierre-Louis. Also, after the webinar, if you have any questions, please write to us at support@reactall.com, and we will make sure to answer your questions or forward them to Pierre-Louis to address your questions. In total, the webinar should be around 30 minutes, 45 minutes. For those that do not know Technobis, we are a Dutch company located in the north of the Netherlands, a world-leading technology provider for reaction screening, process development, solid-state research, and formulation. Many of you know us from the crystallization systems portfolio. You have here our products, Crystal Breeder, Crystal 16, and the crystalline. But today, this talk focuses on the second portfolio of Technobis, the reaction screening and the ReactALL. For just a brief introduction of the ReactALL, for those that do not know yet, the ReactALL is a multiple reactor system with automated sampling. That's the beauty of it. Samples are immediately quenched, diluted, and transferred to standard HPLC LCMS vials on the ReactALL. Then you can take your tray and perform the analysis by LCMS. It is the instrument for reaction screening, scouting, optimization, reaction kinetics, profiling, and I'm very sure that you'll hear more from our presenter today about this ReactALL, and not only. Now, this was about Technobis and reaction screening platform that we have. Our presenter today, Pierre-Louis, is a senior scientist at Sanofi. He was born and raised in Quebec, Canada. He received his bachelor degree in chemistry from University Laval, while being an intern in the research group of Professor Thierry Olivier, focusing on the development of green synthetic methodologies. Then he moved to Montreal, and where he did his PhD under the guidance of Professor Bruce Armstrong at McGill University as an NSERC doctoral fellow, focusing on the development of new approaches to acylation reactions via metal-catalyzed carbonylation and electrochemistry. He then joined the research group of Professor Song Lin at Cornell University as a postdoctoral associate and worked on developing scalable stereoselective electrochemical borylation of oxygenated allylic electrophiles and utilized these methodologies in diverse synthetic sequences to expand the chemistry toolbox. Recently, Pierre-Louis he joined Sanofi as a senior scientist in process chemistry and is part of the data-rich experimentation team. Pierre-Louis, thank you very much for joining us today and bringing this presentation to our viewers. I'm making you a presenter, and I think now you should be able to share your slides.
Thank you so much, Carmen, for the introduction. So today it's my pleasure to be presenting some of the work we've been doing at Sanofi and how we could use enabling technology to develop very interesting reactions. So today I will be discussing Aldol reaction and how can you streamline the process development of those very interesting transformations that can be quite finicky, especially in terms of the stability of those products. And it will be developed using the ReactALL developed by Technobis. So for this presentation today, we were interested to reach those type of moieties, so alpha-hydroxy acids, using simple reagents and transformation and methodology. So essentially, alpha-hydroxy acids are quite an interesting class of therapeutics, and they're pretty useful as synthons. So we can find them in a very large amount of molecules. And another reason why we want to access those moieties is they're very useful as synthetic intermediate. So they can be used in a very large amount of transformation, such as, example, cyclization, formation of heterocycles, or simple endpoint transformations, such as amine bond and alpha amination, for example. And if we're just looking at this structure or this moiety, there's a very large ways of making those type of moieties, and essentially with those various type of transformation. In our case, the target of alpha-hydroxy acid, the Aldol reaction, was quite interesting, since we could simply react a ketone with glyoxylic acid to access these alpha-hydroxy moieties. So it was making sense to make this connection here through an Aldol reactions, which is perhaps the simplest way of accessing those type of cores. But if you look at the literature, and more specifically at Aldol reaction using those synthon here, as we can see, is that even if the Aldol reaction is one of probably the most well-known transformations, especially it's been teaching organic synthesis for multiple years, they can be quite challenging, as they have very variable yield coming out of those transformations. And sometimes the conditions are not very well understood in terms of what are the best conditions, and sometimes the yields are very low, sometimes they're higher, and there's a certain gap to fill here to really understand the kinetics of those transformations. And just as an example, and this is an Aldol reaction we're trying to perform here, as we can see here, this transformation didn't work particularly well using, example, a base and in water. So while the conditions are very attractive, because you're essentially conducting organic synthesis in very benign solvents and using very simple reagents, the yield of those transformations were fairly low. And once you were about to scale up those transformations, the performance of the reaction itself was even going down. So why are those Aldol reactions challenging? Well, in this case, you typically, when you see this product of transformation, there's already something you can tell yourself, where maybe this alpha-hydroxy group start to be very labile in the structure. So to stop at the addition or the Aldol addition is very difficult or very challenging, because in the presence of a base or in the presence of other things, multiple other mechanisms can happen and essentially leads to the degradation of the product. So you can see by the addition of a base, you could have elimination, and then, example, having cyclization or a further Aldol addition, which really complicate this transformation overall for both yield and isolation and purity of the product obtained. So essentially looking at this transformation particularly, we can see that it's very attractive. So it's very benign, cost efficient, and it's just combine and stir in most cases. But as I just explained, the lack of selectivity, low yield, and product stability makes this process very challenging to implement on scale, because the outcome is very difficult to control. But if we look at the literature, as I mentioned, there's a big lack of optimization in kinetic data. Alternative conditions also are not viable. So for this particular transformation, example, weaker base are very challenging, doesn't lead to any product. So it's very difficult to optimize this specific set of conditions. So then you could turn to a different type of Aldol reaction, such as, for example, like Mukayama Aldol, but then you start to add steps to generate essentially a series of intermediate, and then you add more steps to the synthesis, so it makes it challenging to keep it in a route, for example. So really, what we observed there is there was a certain limit to transitional optimization methods. It was very difficult to optimize this transformation with this very limited set of conditions we could use. So we turn essentially to try to use enabling tools to have a better observation of the behavior of this transformation. And by using automation, that we think that we could help us to really capture how the kinetic of product formation and product degradation for this transformation, and really give us more insights on how to control those type of transformation. So the ReactALL is a very interesting tool that helps us to do so, because you essentially have a platform that gives you medium throughput automation that help us studying those type of transformation. And it provides a series of tools that allow you to control, example, dosing of reagents, controlling the temperature, and also essentially sample through some auto sampling through 5 reactors. So then you can generate your sample for kinetic analysis, for example. And also it's very simple because you can use a different quench and rinsing procedure. So it has this quick way of changing set of conditions for quenching for your sample preparation, for example. So the first thing is to look into what's going on to this transformation. So this is example, one of the isolated product of this reaction. So it's mostly pure. We have product, a little bit of impurities in that case, but if you look at the HPLC, this trace looking pretty good. So it was this temperature sensitive. So what is going on? Is it because we work at room temperature, or like we warm up the condition? Is the product decomposing? So as we can see, this is not the case. So even at elevated temperature, this product is fairly stable. Then is it acid sensitive? So we have an excess of glyoxylic acid, and even at elevated temperature with the glyoxylic acid, in that case, we don't see the composition of the starting material. So really what was the problem was the base. So as soon as this product warms up in presence of the base, we can see a rapid decomposition to a series of impurities, and then the product, we lose the product during the time that this is in presence of the base or at higher temperature. So then what we did is we did our first series of auto sampling with the ReactALL to study what's going on with this transformation. So we did sort of a time course study, and at each time point we could evaluate how much starting material and product formation can see over time. And what we can see here is there's a sort of a inconsistency in the sampling in that case. And what we actually observed there is that this reaction is particularly difficult to study through the generation of small samples, and because these samples tend to decompose over time, what if they are taken and sat at room temperature, because of the sitting on with the base, even in the sampling stage, they start to decompose. So we saw this inconsistency due to poor sample stability. So this was very challenging to do so. However, if you use a ReactALL, then you can just simply change your your quenching procedure, and then by just changing the quenching solution, you can see that now the data integrity is much better. So we just changing the quenching bottle and add a 0.1% formic acid mixture to our acetonitrile shell water. And then in that case, it's enough to quench the reaction. And now we can see that the sample that are taking during the day and the sample that are taking overnight, they keep the same kinetic profile or the same reaction profile, because the sample now doesn't decompose anymore. So this was the first thing that we observed there, is that the analysis could be very challenging, because even if you were to just take a sample and analyze this immediately, just the fact that the sample warms up in presence of the base was enough to lose important information on the data. And we can see here the last data is a comparison between sampling by hand and sampling through the ReactALL. We can see we have a loss of approximately 15 to 20%, because by the time that you take the sample and make an example of HPLC vials, it warmed up and it already decomposes in the process in that case. On the harder end, the ReactALL allow us to take the sample at low temperature and then quench it immediately, so then you don't lose the information because it's not in presence of the base anymore. So this in this way, we have a better way of observing our reaction in situ using the ReactALL because of the quenching procedure. So now we have very nicely reliable kinetic data that we can get from this reaction. And the first thing is striking is that this reaction should give you a pretty high yield after just a few hours in that case, if you have a quenching procedure that allow you to really capture the formation of the product. And we can see that without the quench, we have the HPLC profile is much more messy compared to the quench of formic acid. We have a much more reliable way of studying this reaction, and the product formation is also higher compared to the impurities in that case. So now with the right tools in hands, we can then do a lot of different kinetic data. So we can max out our reactor here, and then we can compare a lot of different variables into this transformation to really understand how this reaction works. So we can see that changing concentration here didn't necessarily help this transformation. However, increasing concentration help us to reach a maximum yield slightly earlier compared to a more diluted reaction. However, the loss of mass balance was a little bit more pronounced in that case. Moving on, so the effect of the reagent, we just try to do different things, such as increasing the amount of base and the amount of glycolic acid. And what we can see is that with higher base, again, you reach your maximum at the earlier reaction time in that case. And if you have too much glyoxylic acid, it makes sense. You don't have base anymore because it's called quenched by the glyoxylic acid, and you have no product formation in that case. And again, more base leads to a more steep decomposition of the product after time, so you lose a lot more mass balance. Something we wanted to look is the change of the cation in this transformation. So using a different metal hydroxide, so sodium hydroxide, potassium hydroxide, and lithium hydroxide, for example, were not as performant. We can see that using sodium hydroxide leads to lower yield and also a lower maximum, but reach this maximum a little faster in this transformation. And the lithium hydroxide also the same thing, a little faster, maybe kinetic transformation, but a lot more decomposition, and then they reach a lower maximum overall. So the potassium hydroxide was still optimal in this case. And I think what was even quite interesting here is that the reaction time is very dependent on the reaction temperature that you're using. So by using the ReactALL here, you can have up to 5 different reactors. So you can have up to 5 different temperature that you can screen in parallel. And this is a good way to see how your reaction behave at different temperature in that case. So we did from a range of -10 to 20 degrees. And if you compare those kinetics, is quite interesting, because even though you would compare, example, traditionally everything after 16 hours or so, what you will observe is that room temperature is very bad, and perhaps -5 is really good. However, this is not necessarily relevant at one data point. If you look across multiple data points, so 18 data point, for example, you can see that the room temperature could perform pretty well, but you'll have to stop it after about 30 minutes compared to reaching the maximum yield, example, at -5, you will need at least between 6 to 10 hours, for example. So this is what particularly very interesting for us to really understand that if there's a variation in temperature, example, on scale, then you will need to know what's the range of time where you will still have a pretty good reaction conversion, and you will not have a loss of an important loss of mass balance. So again, another thing that we can do is to compare progress of impurities. So if you look at the reaction profile at -5 degrees and 20 degrees, you can see that there's a pretty good control on terms of impurities in that case, and we reach maximum conversions at about 13 to 15 hours in that case. But at room temperature, again, you will reach your maximum yield at about an hour, 30 minutes to an hour, and then you will, after this, you will start to have very complex mixture developing. So you can really track the formation of impurities that are showing up at 20 degrees. So then this gave us a certain inspiration about how we could tackle this reaction a little bit differently. And perhaps what you want is not necessarily let the base sitting with your product. So one thing we can do is using the dosing unit. So in that case, you could have a dosing unit holding an acidic solution. So then after the reaction is done, you can immediately quench it at -5 in that case. So you can program this using the ReactALL, so an auxiliary of the ReactALL in that case, and then program those quenching using this dosing unit. And so we look at different type of acids in that case. So you can see that citric acid, HCl, and example sulfuric acid are pretty common. And what we observe is that they were working, but they were not giving necessarily high yield or high purity at the end of this reaction. So something that is pretty convenient is that by addition of acid, you generate essentially the product, and it crashes out of the solution since it's not deprotonated anymore. And then you can just do a simple filtration. But then moving to acetic acid, so a little bit milder, in that case, what we can see is we could improve yield and selectivity of this transformation. And we narrow down to about 15 hours where we could get between 11 to 15 hours where we could get higher purity of the compound and higher yield. So we reach essentially this next milestone where on smaller scale or ReactALL scales, we could now improve the yield to 70% with very high purities of the compound. So we stopped after 15 hours. We quench with an aqueous solution with a mixture of acetic acid at -5, and then making sure that the pH was adjusted. So this micro-optimization at between 3 and 5 to help through recrystallization process from the water. We could get, after 2 rounds of recrystallization, we could get about 3 to 5% left in molar liquor, and then overall we got improved yields and purity for this transformation. So moving on, another aspect that is very important is how does this translate to other state-of-the-art equipment. So a lot of process chemists will be aware of, example, the EasyMax is a pretty useful platform for process development in that case, but it's a much larger scale for the most part in that case. And what we can see is going from the ReactALL to a higher scale instrument, we can reproduce the exact same kinetic profile. So that's pretty useful. And then on 3 grams, we could reproduce the exact same transformation, have about the same yield and the same purity. So this is very useful for moving from smaller scale screening to medium scale screening and then larger scale screening. All of the data are followed and the kinetics are also similar. But then we were curious to know what is the rate of the decomposition of this product using different bases to really know how can we limit the amount of impurity that are generated in this transformation. So as we can see, we can use the ReactALL again using this, and then we can deliberately follow the decomposition profile over across the reaction time. So one thing we wanted to do is to see if we can limit the product exposure to the base. So then again, using the dosing unit, so the ReactALL in that case, can we run a reaction at higher temperature that will have faster kinetics, but you just limit the amount of base that you add in this solution by having a slow addition. And again, comparing our impurity profile, we mentioned at 20 degrees, so we can see that we have a fast generation of product, but also quick generation of impurities, and then eventually decompose. You can see that this profile has been slowed down a lot by essentially just adding slowly your base into this solution. We can slow down the production of the product and also really slow down the generation of impurities, even at higher temperature in that case. So this was a direction that we were initially looking for that is still undergoing. So we're trying to see if we can do something, example, in flow or having slow addition of the base to prevent decomposition of the final product. Another thing that we studied was the decomposition of the base against different bases. So we try having less strong bases, such as, example, organic bases, TEA or TBA hydroxide, and also other inorganic bases. And what was very interesting is that a weaker base, such as potassium carbonate or triethylamine, really slowed down the decomposition of this product. So we're curious to know, is this viable in this transformation, and is a weaker base viable in this transformation? And you can see that the TEA was very interesting because the impurity profile was very low. So at first, TEA was not working very well. So you can see that if you were to just do a simple screening reaction, you'll repeat this, use TEA, potassium carbonate, and it doesn't work. And then most people will just move on. And then you will probably miss an opportunity, because then if you were to just follow this reaction with the ReactALL, it's an automated platform. So if you leave it for 3 days, it doesn't matter, because it does the work for you, which is perfect. So it collected samples over 3 days. And then we can see that it's just because this kinetic is very, very, very slow. So at slightly elevated temperature, and if you live for long enough, you will see a good amount of product formation and not a lot of impurities. So actually, this was a very interesting set of conditions for this reaction. And if you were to increase the temperature now, you can see that also the impurity profile is much better. So this now tolerates higher temperature by moving to a less potent base in that case, and that we can have a high product formation and a better reaction profile by doing so. So that inspired us to do a high throughput screening of different amine base in this transformation to really see which base is more performant. And we saw this base B9, so tetramethyl piperidine base here in that case was very good to lead to a almost perfect reaction outcome by having a 76% LCAP and mostly starting material left, very low amount of impurities in this transformation. So that was pretty performant. So with this, essentially, we can see that by using the ReactALL, we're able to go from a process that was going from 45% yield to 70%, so increasing yield and purity profile of the product in this Aldol reaction. So really, the ReactALL would allow us to have a precise control of the reaction condition, a precise quenching and sampling, and also was automated. With all this, it was very easy to do essentially some early process development of this transformation. So then with those tools, it allowed us to improve the yield, improve purity, investigate kinetics, and have a higher, essentially understand the stability profile of this transformation for this product. And that allowed us to think and leads to different new directions. So we saw that the quenching procedure was essentially very key in this transformation. So understanding the kinetics of when to quench and how to quench this transformation. And the slow addition of base and the amine base are two different directions that we're currently studying for the outcome of this transformation. So it really helped us to find new direction into this Aldol and not give up too quickly in that case. So this is the end of this presentation. And of course, I would like to thank the team that worked on this project, and also the whole Sanofi US process chemistry and engineering team that have been working all together to implement new technology in our labs. And with this, I will be very happy to discuss further and ask and answer any question that you may ask.
Thank you very much, Pierre-Louis. Very much appreciated and enjoyed your talk today. We have a few questions as well, I see coming. I was just before you mentioned going from 300 milligrams to 3 grams, I was thinking, without giving any names of any other platforms, there are a lot of labs out there that they still use the round bottom flasks and so. But usually, reaction kinetics would be done if you do not have the ReactALL on a larger scale, right? what is, you are now at Sanofi, but you were in other labs in your career. What is your feeling there? So if you do kinetics, at which scale would you do that?
Yeah, I mean, it's a very interesting question. So typically, like back in my former research, like we will always do kinetics. Like sometimes you will do not necessarily like in a very special way. You will have exactly like you say. You have your typical reaction flask. You have a round bottom flask. It could be a tube. It could be an MR tube in that case. So sometimes you can do example kinetic in an MR tube, but then you need to think you need to have a very expensive like an MR machine, change temperature. It can be very complicated. And then is an NMR tube experiment going to translate to an actual scale-up process that's going to be, for example, stir the exact same way? So when you move from a very small reaction to a large-scale reaction, you start to see very different things. It's not the same game anymore. So you might not see the same reaction profile at all. So I think that the key thing and also you have to be there for the sampling. So if you do even a large scale, you need to be there sampling with your syringe or your pipette. So someone needs to do it for you, or you have to do it for yourself. And then you need to respect a very tight schedule to do so. In the industry now, we are busy to do very different things. We have meetings, etc. So having automation really help us to be on schedule. So your data points are the same across all the reactions. So they're very comparable time-wise using this automation. So I think that, and also you need to have a set of conditions that can translate better to larger scale. And something I didn't show here is that the ReactALL use, example, an impeller stirrer, which impeller stirrer are more likely to be used on larger scale in that case. So this kind of continuity of resemblance between small scale and large scale makes it a little bit more reliable to understand if the reaction profile based on both chemistry and the essentially the hardware device that you use to run this reaction makes them more comparable.
Yeah. Thank you for this. Yeah, I was just talking this week with somebody at a conference that I was in the beginning of the week, and a user also of the ReactALL, and put it quite nicely, saying that was saying to me that ReactALL brings the throughput from, at a certain extent, from the high throughput, and the reliability of the data from the low throughput. So kind of in between, you are mixing it at medium throughput, let's call ReactALL, this key feature. So I just wanted to take your opinion also on this.
Exactly, and it's a good way to just simply, you don't need to have multiple gram of material to get your data. You can still work on small scale and have this reliable kinetic profile from medium throughput to higher throughput. Essentially, kind of what I was demonstrating when I went from the smaller scale to bigger scale with a different instrument. They were very comparable. So that's very good.
Good also for us to hear that. And now, because we were talking about scale and so, but now, and also one of the questions here, somebody is asking, how efficient is the sampling when the reaction solutions are slurry or non-homogeneous? So, heterogeneous reaction. What are the troubles that you can get there? Do you get troubles less or more than the usual?
I can give the honest opinion right there.
Yes, please do so. But, we are all chemists in the lab, so there's no ideal world, huh?
Yeah, exactly. I mean, there will be. The good news is that I did work with. Here was homogeneous reaction, but I did work with other transformation that were heterogeneous. And for the most part, I was surprised it was very reliable. Even like, for example, you have an organic solvent and an inorganic base, you will have the sample, it will work. And I never saw any issues with heterogeneous for the most part. However, I know that once in a while, like there could be issues with if you have small particle it could get aspirated and it could potentially get to a clog. And this didn't happen very much. However, recently, I think Technobis is working on having some filters. I don't want to speak in terms of telling what Technobis is doing or not, but there's a filter adapter that you can put at the bottom of the sampling that we've used also, which can help also preventing clogging in the later tubing. That is a little bit more annoying to fix if this happens. But in my experience, I didn't have much trouble with heterogeneous reaction for sampling. It was fairly reliable.
Indeed, we do have these fritz now of different pore sizes nowadays. I think they were introduced this year, if I'm not totally wrong, on the market. Glass type of fiber, and so also to stay away from any type of chemical reactions that you might or interactions you might have, and so and also to be able to easily dispose them as well. Somebody else has a question. Why is one reagent in excess?
Yeah, I think it's the glyoxylic acid. So in that case, let's go back to example. I'll just look at some kinetic here. So one reagent is in excess simply to help this reaction go a little bit faster. I think I did a comparison right here. So essentially, glyoxylic acid, we changed the concentration. Since it's a very cheap reagent, it's simply to help. So if you have a higher concentration of your electrophile, then it's really to try to push for a higher conversion, a faster conversion of this transformation, because you have to keep in mind that you want to stop this reaction as early as possible, because the moment the product sits around the base, you're going to start to have a loss of mass balance, for example. So on this slide here, you can see that lowering the amount of glyoxylic acid, it's hard to see because I unfortunately use the same, very similar shades in that case. The reaction profile looks very similar. But because glyoxylic acid is a commodity chemical, we've just decided to add more equivalent of it, and it doesn't change the outcome of the purity because it stays in the water, and when you quench this transformation, this product crashes out of solution. So then you can just do a filtration, essentially, and can even recrystallize the mother liquor to get even more product out of this without worrying about the glyoxylic acid contaminating the product, for example. So the reason why we went for 3 equivalent was really simply to make sure that the reaction will go to completion as fast as possible, even if the reagent get depleted. However, on the ReactALL scale, we didn't see a big change of having almost 1 equivalent of glyoxylic acid. So it was just a preference, just to making sure that the product formation will be complete.
Thank you. Can you comment on definitions of yield and weight percentage? Do these values need to be multiplied together to obtain mass of desired product?
Very, very good point. I didn't precise here. The yield in that case here was the adjusted potency yield. What does that mean is that it's actually the crude yield times the weight purity. Weight purity is essentially a quantitative NMR that was analyzed of the sample against a known standard, a known mass. And so by NMR, it was 93% pure. So by weight, it was, essentially by weight, it was 93% compared to the standard by NMR. And this was multiplied to the crude yield to give that 70%.
Okay. Somebody says, I missed parts of the talk. Have you tried organic bases?
Yeah.
Yes.
So I can just jump to I will jump toward the end. So there was a very interesting discussion here with the organic bases. So at first, in this story, was mentioned that the base, so organic bases such as TEA, are a little weaker. So I just want to show this slide very quickly.
Yeah.
So the point was made that if you were to look at this reaction early on, comparable with the KOH, you would have missed probably this data point, but actually it was working pretty well. So you would not have a high impurity profile, but the reaction was very, very slow. So in that case, we moved to higher temperature transformation, and we screen a little bit more of the bases, so amine bases, to really try to see what reaction leads to a better reaction profile. And what we found is that TEA and this pyridine base was very good for this transformation, and there was a much better reaction profile. So we can see from the trace here, there was much lower impurities at the end of this transformation and keep high conversion. So we're still working on seeing if we can get full conversion out of those amine base.
Somebody has a question regarding the automated sampling dilution. Oh, maybe this is for me actually. How is this technically working? If the probe is stuck or the probe is sucked in through the tube. I will try this one. Indeed, the sampling takes place through the tubing to a shaft that is really exactly in the middle of the smart cap in your reactor, and around this, I do not have really a picture now with me, but around this shaft that is in your reactor, so in contact with your reaction, is also you have your stirrer, so it's mixing. When you take a sample by making use of nitrogen and changing pressure, then the sample is, as Pascal was saying, is sucked into a pocket in the smart cap. Then the valve closes, and from the side through this smart cap comes the quench and the dilute. So immediately your sample is also quenched, diluted, and pushed by making use of nitrogen through the lines directly by the needle into your HPLC LCMS vial. At the end of the sampling is also more nitrogen purged through the lines to make sure that all the sample is in the vial, and also nothing is left over. Of course, also after sampling, you also have a rinse step, so to avoid cross-contamination from one sampling moment to another one. And maybe something very important also to mention, there are 5 reactors, 5 needles. So there is impossible to, and 5 individual lines, so you will not cross-contaminate between different reactors as well. It's quite added value. You received a few congratulations and very good presentation also, Pierre-Louis. Thank you very much.
I don't see the message, but that's very kind audience. Thank you.
Somebody is asking again about sampling, suspensions. Well, we talked about heterogeneous mixing. I think we addressed that. I think we are closing. We should close now. We are bit more over the 45 minutes, but I think we also took most of the questions. I would like to thank you, Pierre-Louis, for your time, for putting this presentation, these slides together and showing them today with our presenters. I would like to let you know, our viewers today, that next webinar on ReactALL related will be on the 16th of April with Trung from Pfizer on other process development features and reactions performed with the ReactALL. If you're interested, stay tuned. We come back in less than a month with another webinar. Until then, thank you very much all. Thank you, Pierre-Louis, once again, and have a good day. Still a long day for you.
Yeah, there's still quite a bit of time. Yeah.
Yes. Thank you. Bye.
Thank you.